is progressive wave? Clear, everybody?
Yes, sir.
So suppose you see, if you take a water, if you put a stone on water, the waves can travel in any direction. So that is what, which is carrying the energy in any direction. That is what we used to call it as progressive wave. What is the wave we used to say? Progressive wave. So once it will hit the hard surface, any kind of hard surface, then the reflected wave will overlap that initial wave. Then that is call it as, what is the wave is to say? Yes, please, stationary wave. So then a stationary wave, or you can say it is also call it as standing wave. So then if it is making overlapping the incident waves, then that is what it will form two things. One is nodes and another one is antinodes. So nodes means where minimum displacement, either zero or minimum displacement, or maximum displacement, which we used to call it as nodes. Antinodes. Antinodes, maximum displacement, minimum displacement, nodes. That is what you have to remember. Is it okay, guys?
Yes, sir.
Yes? All of you? Yes? Now, Sanjay, that
Yes.
question what we have done is a mistake. Now I am going to teach you. So please note these 2 points. Now you all can modify that. So what is the distance between two successive crust and two successive trough? I want to know, everybody.
Two
Two successive crust or trough, what is to call, everyone? Yes, this is
lambda.
crust and sorry, this is trough. Trough and this is also trough and this is crust. So the distance between two successive crust, what is to call, everybody? Wavelength. So this is the wave which we used to call it as progressive wave. What is the wave which we used to call? Progressive waves. So in progressive waves, the distance between two consecutive crust or trough or compressions or rarefactions is called it as how much? What is that call it as? How much Ra? Either compression to compression or rarefaction to rarefaction or trough to trough or crust to crust, consecutive trough to trough or crust. We used to call it as a what? I want answer from the people, which we used to call it as wave. Okay, so wavelength. Now coming to the nodes and antinodes. So then in stationary waves, so please note it, crust to crust or trough to trough, consecutive crust and consecutive trough is side by side, which we used to call it as lambda. Okay, everybody, or between two compressions or between two rare fractions. If you take a stationary waves means what? One reflected wave and another one is what? Incident wave. So it is coming back. So progressive. So this is what we used to call it as progressive wave. So node, antinode, no, antinode, and node. So here, please remember, you can take down also, nothing wrong. So the distance between two consecutive nodes are antinodes. Nodes are antinodes. So please remember that. Distance between two consecutive nodes, or you take it as a antinodes, is not lambda. It will come. What is that, everybody? Yes, please. Consecutive nodes or antinodes is lambda by 2. So this statement. Distance between two consecutive nodes are antinodes. Antinodes. Antinodes is lambda by 2. Okay. Then distance between two alternative nodes. Distance between two alternative nodes or antinodes. How much it is? Anybody? Antinodes. How much it is? Suppose this one I'll take, another afterwards I will take this one. So by that time, what is that? If from here to here, lambda by 2 means, then here also lambda by 2. How much it is? Lambda by 2 plus lambda by 2. Alternative. Alternative means it will become how much, Ra? Next one again this one. So now from here to here, node to node, lambda by 2. Then from here to here also lambda by 2. So now this and this is alternative. So lambda by 2 plus lambda by 2, which we used to call it as a what?
Lambda.
Lambda by 2 plus lambda by 2, how much, Ra? Lambda. Am I right or wrong? Yes, please.
Yes, sir.
Yeah, lambda by 2 plus lambda by 2, 2 lambda by 2. 2 will get cancelled, will get lambda. Okay. So distance between two consecutive nodes or antinodes, lambda by 2. If I take this one, again from here also lambda by 2. So this lambda by 2 plus lambda by 2 will become lambda. Is it okay, ma? Girls? Boys? Sam, understand? Prudhi? Abhirami? Mr. Darshan? Everyone?
Yes, sir.
Yeah. So
Yes, sir.
distance between crust to crust, lambda, node to node or antinode to antinode, lambda by 2. So that is what you have to remember. Okay. So this is what is about it. Now we are going to study what is the velocity of the sound in gas and what is the parameters which is present. So as we know, sound is generally we are all hearing the sound through what? Through air. That is only the medium. What is the medium? Call it as. We studied. Everybody can tell me what is that? Yes, please. We all know that. Yeah. So that is what. So let me take velocity of a sound. So velocity of a sound, that is what transmission of a sound. So it is depends on material. So medium. So we all know we are having three different mediums. Solids. Next one is what? Liquids. And next one is what? Gases. So solids, the sound will travel the maximum speed compared to solids. If you are coming down, the speed of a sound decreases or increases? Speed of a sound decreases or increases? Everybody, decrease. So in gases, the sound will travel with the least speed. But that is only our concept because we are hearing the sound through what? Everybody, through gases. So that is what is velocity of sound. So till now you might be studied different things, velocity of a sound. So generally what is the wave speed formula? We all studied that. Wave speed formula, what is that? Lambda by time period or lambda into frequency. Both unit is what? Meter per. Wave speed, what is the unit, Ra? Speed unit, meter per second.
Meter per second.
Yes or no? That is what. Now, we are going to study velocity of a sound. So here we all will experience completely new things. So just have a glance and attend to mine. Definitely everybody can understand. It's not a small beginner. So velocity of a sound in different medium is different. That is what we know. Sound travel in different mediums in different. But in a given medium, its value is constant and it depends mainly on two properties. Anybody can tell what is the two properties? Sanjay? In a given medium, sound is remains constant. Am I right? For example, if I take air at a given temperature, it is remains constant. If I take iron at a given medium, it is remains constant. Am I right, guys? Please respond. All of you?
Yes, sir.
Yes. So it is producing what wave? Transverse wave or longitudinal wave? Yes, please.
Longitudinal wave.
Longitudinal wave, always. Okay. So now you see that. So if you have been taken a velocity of a sound, is basically it depends on two things of a medium. Okay. Velocity of a wave depends on two, okay, two properties of a medium.
Temperature.
Yeah, two properties of medium. Temperature we studied, that is forget about it. Here, properties of medium. So one is elasticity. Sanjay, are you catching now? There is a guide, there is a word. You remember? And density. Elasticity and density. So if you open your guide, can you tell me the page number, Sanjay? Let them see that. One question answer they have given depends upon the elasticity of the iron. Am I right? One response. Others they never seen. So that's what. So it is depends on two things. One is elasticity and another one is what? Density of the medium. So if the medium is homogeneous, if the medium is homogeneous, so if the given medium is homogeneous, so density and as well as elasticity remains same, or it will change with the direction. Everybody, yes, please. If the homogeneous means what? Ninth class chemistry you all studied. Homogeneous means what? Same type of particle. So density and elasticity do not change. So you can go any direction. Do not change with the direction. So it will not going to change. And the velocity of a sound remains what? Do not change with the direction. So velocity remains. Speak. Velocity remains constant. Okay, so that's why in solids, particularly if you take the velocity of longitudinal wave is basically greater than that of transverse wave. So, because if you notice it, like if you take in the case of earthquakes basically what waves? It is a shock waves, seismic waves basically. So once the seismic waves are produced during an earthquake, which basically they are the longitudinal in nature, but when it will reach us to the seismic station, clear? And then first they will reach us to the seismic station, and then the secondary shock waves, which are transverse in nature, they will reach the seismic station later. So inside, somewhere deep inside the earth, the happens. So from that point, the station which is present, mean the point, the earthquake zone. So first see that which waves will which wave reaches first? Seismic waves, the entirely seismic waves only. Earthquake waves we used to call it as seismic waves. So now it will be two kinds of waves. One is longitudinal waves, energy, and another one is transverse wave. So which will reach us to the first to the seismic zone, seismic station, everybody. The point where we are detecting. Yes, please. This is the seismic station. So which wave will reach us to the first, longitudinal wave or transverse wave? Longitudinal wave. Do you understand, everybody? Longitudinal waves. The earthquakes which are longitudinal in nature, they will be detected by first because they will travel greater than that of transverse wave. The velocity in solids, please note it. In solids, which way will travel faster? Everybody. Velocity of longitudinal waves. Velocity of longitudinal waves is greater than transverse wave. Clear, guys? Please respond, guys. All of you? Yes. So based upon this observation, so like elasticity and as well as density, Mr. Sir Isaac Newton is given a mathematical expression for the velocity of a wave in an elastic medium. In an elastic medium, so what is the wave speed is equals to root over E by D. This is the mathematical expression which is derived by Mr. Sir Isaac Newton. So here, V is the velocity of the wave in the medium. Velocity of the wave in the medium, and E indicates elasticity and D indicates density. So please note it. Elasticity and D indicates density. So you can calculate the elasticity. Nothing is there. Earthquake will be produced at somewhere deep inside. So it will produce both longitudinal waves and as well as transverse waves. But the detecting center, if you take the seismic station where we are detecting the earthquake, 8th class you might be studied Richter scale and all. So which waves we can reach us to the first? That is longitudinal waves. And then afterward only we can detect the transverse waves. Understand, Amma? Because solids, longitudinal waves will travel faster. That is what. So this is the mathematical expression which is given by Mr. Newton's for calculating the wave speed. Okay. based upon the two parameters, that is what? Elasticity and density. So in case of solids, please remember, elasticity is measured with the symbol Y in case of solids. In case of solids, elasticity. Sam, are you there? Elasticity is measured, okay, in case of measured by its Young's modulus. Young's modulus, which is the symbol, call it as Y. Okay, capital Y. Capital Y indicates Young's modulus. Please remember, and so that I can replace in place of E Young's modulus. So velocity of the sound wave, which is equals to root over Y by D. This is the formula for calculating velocity of a wave based upon the elasticity and density. So anybody having a doubt, you can ask me, please. Clear, guys? Okay. So now if you compare solids, liquids, and gases, so in which medium sound density is maximum? Everybody, in which medium density is maximum? Yes. In which medium density is maximum? All of you.
Solid.
Solids. That's why the velocity of the sound is, which medium it is maximum? Solids it is maximum, less in liquids, and least in which medium?
Yes.
Least in gases. That is what you have to remember. So the reason is the density of the solids is greater than that of liquids and of gases. So that's why the elasticity of the solids is many more times larger than that of liquids and gases. So please note it. The elasticity is many times greater than the solids and liquids and gases. That's why it is more. So the elasticity and density is more in solids, less in liquids, and least in gases. So that's why please remember, the velocity of a solids is greater than velocity of a liquids is greater than velocity of gases. So when we are moving from elasticity of the solids is more times larger than the liquids and gases, so the speed is decreasing. Decreasing order of velocity of a sound is this one. Clear, everybody? All of you? Yes? All of you? That is one. Now, if you comes to in case of gas, this is last time, I'll start. In case of gases, see now this elasticity and density for what actually? We studied for what? We studied for what? In solids. Okay, that is what. Now in case of gases, if I take a gas, so in case of gases, if you have been taken, later I will give for liquids also. So please remember, in case of gases, the elasticity factor for gases, elasticity depends on pressure. So that is why elasticity is purely depends on pressure. So that's why the expression for velocity of a wave in a gas. In gas, can you tell me what is the expression for velocity? Root over elasticity depends on pressure. So it will become P by D. Is it okay, guys? Understand, Mari? Because it is depends on pressure. In gases, elasticity depends on P. In solids, elasticity depends on what? In solids, elasticity depends on what? In solids, elasticity depends on what? Young's modulus. So that it is Y by D. In gases, elasticity depends on pressure. So it is P by D. Is it okay, guys?
Yes.
Yes, please. All of you? Yes, that is what. So P and D are the pressure and density of a gases. So this is what you have to remember. So now, Sir Isaac Newton assumed that sound wave propagates through gas and the changes that takes place in volume. The volume of a gas is actually isothermal. Means he assumed as the gas which is at isothermal process means constant temperature. Isothermal means, please note it, constant temperature he has been considered. So, but it has been proved wrong. Temperature also changes. So the velocity of a sound in a gas is assumed by and calculated actually by Newton. It is approximately 280 meter per second. 280 meter per second, where later it is actually wrong. It has been, he has assumed that it is a constant temperature. So, but later it has been proved wrong. Now, presently, what is the speed of sound? Everybody in a gas, air. Everybody, we all knows that. How much it is?
340
340 meters approximately. So, Newton's, he has assumed that it is an isothermal system and he has calculated that the speed came around 280 meter per second. But later it has been proved mismatch. It is observed that the value is experimentation, it is about 340 meter per second. So that's why it is later it has been proved that Newton's even it is expression, the speed is wrong, it is okay. So it has been considered at isothermal process, but it has been proved wrong. So the velocity of sound in a gas as assumed by Newton's and calculated from his formula is found to be wrong and it is given wrong value. So later it has been calculated, that is. So till here you study, and then from here velocity of a sound in a gas based upon the temperature, based upon the molecular weight, based upon the density. Okay, these are all the things we are discussing in the tomorrow's class. So because density of a gas matters, weight of a gas matters, because we are having different gases. Does not having one different. We are having varieties of gases in our surroundings, and temperature is also matters. So based upon this and all, we'll discuss in the tomorrow's class. I hope you all learned something new today. Everything I think very interesting. See, actually physics will be like this only. If you keep on studying, more you will learn. Definitely 11th and all, it will be very familiar to score well. So 11th, everything will be keep on making you keep on learning only. Every factor is important now. So this is what about it. Anybody having any doubt, please ask me. From here, we'll continue. And even tomorrow, I'll teach you Doppler effect also. So maybe heard this Doppler effect somewhere, but we'll discuss tomorrow. Okay. Thank you, everybody. We'll meet tomorrow.
Thank you, sir.
Yeah, thank you.